Snow problem. Improving SWE estimates using Bayesian analysis. In the western United States, 75% of water supplies come from snowmelt. The Colorado River alone provides water to almost 30 million people. Water resource managers must accurately estimate how much water is stored in this winter snowpack to make informed decisions. And before we dive into quantifying the snowpack, it's crucial to understand its significance. One good example is the Glen Canyon Dam, as shown in Figure 2. This dam not only generates hydropower, but also regulates water distribution for agriculture and public use. Effective snowmelt predictions guide reservoir operations, helping to mitigate drought and floods. To assess the snowpack, we rely on snow water equivalent, also known as SWE, a measure of snow depth and density that determines how much water is stored on the ground. Remote sensing offers a basin-scale solution by utilizing electromagnetic scattering to infer snow depth and density, but the physical processes involved are not yet fully understood, which introduces significant uncertainty into these estimates. The alternative, digging a snow pit, provides highly accurate data, but is very limited in scale, as only about 10 locations per day per location can be sampled. The SNOX campaign comes in to save this. It's a multi-year field experiment across the nation, as seen in Figure 3, designed to evaluate remote sensing techniques by combining diverse airborne and surface-based observations. Advances in LiDAR, microwave radar, and spectrometers have improved large-scale SWE estimation, but this uncertainty does remain, especially in complex alpine terrain, where a lot of the snowpack in the U.S. resides. This study aims to improve these SWE estimations by integrating airborne data sources through Bayesian inference and by incorporating terrain influences with a known connection to SWE. To start with our data flow, airborne SWE observations are calibrated against snow pit measurements to generate a sparse 2D SWE field. This SWE field, combined with topography and weather forcings, feeds into the iSnowball energy balance method, a proven tool and open source code for basin-scale water resource forecasting and proven by a 2023 study by Meyer et al. From here, we can derive meltwater runoff estimates, the output that water resource managers are the most interested in. Improving this 2D SWE field is the main focus of the proposed research. The novelty of this study lies in leveraging SNOX's extensive concurrent airborne and ground data for better hydrological modeling. My hypothesis is as followed. If the SNOX campaign datasets have enough concurrent ground observations to compute residuals for airborne observations, then a Bayesian framework and co-kriging will be able to reduce 2D SWE field uncertainty as compared to individual sensor uncertainty in estimating SWE. I propose developing a simple Bayesian geostatistical framework for fusing LiDAR and SWEDAR estimates, using ground observations to compute residuals as seen in Equation 1. Computationally, I'll use Markov chain Monte Carlo implemented in PyMC to efficiently sample the posterior distribution, as geospatial data is very computationally complex. Finally, using co-kriging from the Python toolkit PyGeoStatistics package, we can integrate elevation, vegetation, and slope as secondary variables to generate a continuous 2D SWE field, addressing these high alpine challenges where remote sensing can seem to struggle. I started by looking at the SNOX 2020 data, mapping SWE distributions and the coverage for an initial analysis and dataset feasibility. The likelihood function can be constructed by using the observed SWE from snow pits as shown in Figure 4 as squares, and computing residuals from our observed airborne data SWE estimations shown as points with our color bar to the right for airborne snow LiDAR, and as our orange swath of radar. The SWE estimates for the SWE-SAR microwave radar are in preparation, or can be computed through the open source SNOW microwave radiative transfer model. In my study, by restricting residual computations to locations with concurrent airborne and in situ measurements, about 100 ground observation sites, interpolation errors will hopefully be minimized. Our expected outcome is a continuous 2D SWE field similar to this plot generated at Meehan et al. 2024, which utilized machine learning and ground-penetrating radar measurements from the SNOW-X dataset in conjunction with LiDAR. However, this study's choice of ground-penetrating radar limits its applicability to the future of satellite missions. Prior work, like on the previous slide, demonstrated integrated SWE estimates using GPR and LiDAR can reduce SWE uncertainty. However, our study extends this research by using airborne-only datasets, making it applicable for future satellite missions to enable global SWE monitoring. Secondarily, unlike decision tree-based machine learning, which has been used in a variety of previous studies for interpolation, the choice to use Bayesian co-kriging is motivated by reducing the risk of overfitting, and co-kriging works well with sparse geospatial datasets that are spatially correlated. I anticipate that by combining airborne observations through a Bayesian framework and co-kriging, we'll reduce the overall uncertainty in the 2D SWE field to below 15%, improving on studies that relied on machine learning approaches and ground-based methods. In conclusion, new SWE observation techniques justify research into generating state-of-the-art input parameters for meltwater runoff models. Our results from this study will inform combining airborne sensors for future satellite missions that will go on to get global SWE monitoring. And finally, informing water resource forecasting is an important goal in the face of exacerbated floods, droughts, and imminent water resource uncertainties. Thank you. See my references on the next slide, and this presentation is published to my GitHub. Thank you.